Every square matrix n by n has an associated value called its determinant, shown by straight vertical brackets, such as that example there. Okay, right, looks like a matrix. The difference is the brackets aren't hooked, right? They're straight vertical brackets. If you see that, you see the straight vertical brackets, that's telling you I'm going to find the determinant of this matrix, okay? If you look at the examples below in that box, 2 by 2, there's also a DET in front. What do you think the DET stands for?
Determinant.
Determinant, right? Okay, you'll see it both ways, either the straight vertical brackets or the DET out in front of brackets. Either way, it's asking you to find the determinant, okay? Which, again, the determinant is the value of a matrix. When it talks about the value, it lines up with the linear map of when you're using matrices to solve linear equations. That's the association there. But to find the value of a matrix, to find the determinant, we're going to find the difference of the diagonals. We're going to find the difference of the diagonals. What do we find in EJ?
Difference
Of?
the
Diagonals. EJ, what are we finding?
the difference the diagonal.
Difference of the diagonals. Good. All right. So, if you look at this example here, you can only find the determinant, again, if it's a square matrix, okay? It has to have the same dimensions, same rows, same columns. Otherwise, you can't find the determinant, okay? So, top left, difference of the diagonals. So we'll do 1 times 8 is 8 minus 4 times 5 is 20. So the determinant there would be negative 12. Yeah.
I like this. Coach first.
Top right, difference of the diagonals. 1/2 times 2 is 1 minus negative 1 times negative 1/2. It's a positive half. So that answer would be 1/2. Bottom left. What do you think that determinant would be?
I think it's negative 22.
Good. 18 minus 40 gives us negative
Oh my goodness.
22. What?
Why are we unfolding pi?
It's not that big a deal.
Yep. It is.
1/2 times 2 pi. 1/2 times 2 pi is just pi. You can write 3.14 or pi. Minus 4 times 1/8 is 1/2. Which if you subtract that, we'll say is about 2.64. Okay. So that would be the determinant of those matrices. All right. So 3 by 3 matrix. All right. We're still finding the difference of diagonals. Just a little bit longer process. Okay. So here, the first step when we're finding the determinant of a 3 by 3 matrix is we need to repeat the first 2 columns. So we need to rewrite 2, 5, and 10. And we need to rewrite negative 3, 1, and 3.
Why don't we repeat the third one?
Because it don't work like that.
Why?
Because when we do the diagonals, you'll see how it lines up.
Okay.
So again, we're finding the difference of the diagonals. We just have 3 diagonals in each direction. We will start top left to bottom right. So first, we'll have 2 times 1 times negative 1, which is negative 2, plus 3 times negative 2 is 6 times 10 is 60, plus 4 times 5 is 20 times 3 is 60. And then we'll find the difference of the diagonals going in the other direction. So we will do 10 times 1 times 4 is 40, plus 3 times negative 2 is negative 6, times 2 is negative 12, plus negative 1 times 5 times negative 3 is 15. So now add up each side, find the difference. So I'll be 118 minus 43 should give us 75. Repeat the first two columns. 5, negative 3, 2, 6, 2, negative 3. We're finding the difference of what? We're finding the difference of what? Diagonals. Thank you.
You're welcome.
So we're going to have 5 times 2 is 10, times 4 is 40, plus, I love zeros, 6 times 0 is 0, 0 times 2 is 0,
No way.
plus, negative 1 times negative 3 is 3, times negative 3 gives us a negative 9. Difference of the diagonals in the other direction. 2 times 2 is 4, times negative 1 is negative 4. Then I got my lovely 0. Negative 3 times 0 is 0. 0 times 5 is 0. And then 4 times negative 3 is negative 12 times 6 is negative 72. I'm going to add a plus sign in there in a second. I don't know why I didn't. So 40 minus 9 gives me 31 minus a negative 76. So minus a negative makes that plus. So the determinant there would be 107. All right, next part, inverses of matrices. A matrix can have an inverse if and only if it is a square matrix. All right. But not all square matrices have inverses, okay? If the determinant of a matrix is 0, it's not going to have a inverse, okay? Then, if we multiply a matrix by its inverse, the resulting matrix is an identity matrix, which is kind of like getting 1, okay? It's kind of like multiplying and getting 1, but what an identity matrix looks like is it's a little pattern. All right, a 2 by 2 would be 1, 0, 0, 1. A 3 by 3, and the identity matrix would be 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, and that pattern would continue. A 4 by 4 would be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. That pattern will just continue down. Excuse me. Okay, so we have that formula for the inverse of a matrix. You just have to memorize that. All right, it's the inverse of a matrix is 1 over the determinant. Then you flip A and D, and you make B. You multiply B and C by negative 1. Okay, 1 over the determinant. Flip A and D, and multiply B and C by negative 1. Then you distribute 1 over the determinant, and that would give you your inverse. So, if you look at A here, okay, first step, I need to get the determinant. How do I find the determinant?
You do the diagonal.
There it is. Difference of the diagonals. So, 4 times 1 is 4, minus 3 times 2 is 6. Gives us negative 2. So, the inverse of that matrix, to set it up, the formula, I'll have 1 over negative 2, which is negative 1/2. I will flip A and D, So that will be a 1, and that will be a 4 on the bottom right. And then I need to multiply B and C by -1. So that'll become a -3 and a -2. From there, I will distribute 1 over the determinant. I will distribute that -1/2 to each term. And that'll give us -1/2, +3/2, or 1.5, 1, and -2. Okay. So if you multiplied that inverse by the original matrix, if you did rows by columns, what we just did, it would give you that identity matrix 1, 0, 0, 1. Okay. So that is what you would do to identify if matrices are inverses or not. You could multiply them, and if they give you an identity matrix, they would be inverses. Yes. Yes, AJ. So if you look at B, first step is to find the determinant, right? 4 times 1/4 is 1 minus -3 times -1/3 is 1. What's 1 minus 1?
0.
Wouldn't
0.
it be a +1 for the second number because it's -1/3 times -3?
Right, but we're finding the difference of the diagonals, right? So it'll be minus that +1. So,
Oh wait, yeah.
so that gives us 0 there, which means, right, that means there's not an inverse. Okay?
So there's not the same for the next one.
Nope. For the next one, the determinant 3 times -2,
You're right.
-6, and then it'll be -6, which gives us -12. So our determinant is -12. In our formula, we'd write it as -1/12 because it's 1 over the determinant. We flip A and D, so we flip 3 and -2. And then we multiply B and C by -1. So that'll be a -2 and a -3. And then we distribute that -1/12. And we would have our inverse. Boom, shakalaka.